Hello everyone, I am Siddharthan. Currently, we are in the seventh module of our hands-on machine learning course, and this seventh module is all about building machine learning models from scratch. So, in my previous videos, I've explained you what is the intuition and math behind a support vector machine model and how you can reduce the gradient descent for a support vector machine model. And in today's video, we are going to discuss how we can build a support vector machine classifier model from scratch in Python. So this is the agenda for today's video, and in case you haven't watched the previous videos on SPM, I suggest you that you watch all those videos. I'll give the link for those videos in this particular video description. You can check that out. So let's get started with today's video. So I have given the equation of the hyperplane here. So we know that the main component of a SVM classifier is the hyperplane. So we will try to build this hyperplane that separates the data points into two groups, and this is the equation of the hyperplane. So y is equal to wx minus b, where w is the weight of our model and b is the bias of our model, and x is our input feature and y is the label that we are going to predict. Okay, so this equation is similar to the equation of a straight line. So our goal when we use a machine learning model is that we will try to build this equation, build this function in Python. So once we do that, we need to find the best values for our weight and bias. So the process of finding this best value or optimum value for weight and bias, which are the parameters of the model, is called as optimization. And for this optimization purpose, we will be using an algorithm called as gradient descent. So we have discussed about this gradient descent a lot in our previous videos, and I hope that you are clear about what is this gradient descent and how this gradient descent works. So I have given the definition for gradient descent here. Gradient descent is an optimization algorithm used for minimizing the loss function in various machine learning algorithms. It is used for updating the parameters of the learning model. So this is the definition of this. So as I've mentioned here, it is an optimization algorithm. Optimization in the sense we will try to optimize this support vector machine classifier so that we can get better predictions. Okay, so optimized model in the sense our model should have the best parameters value, that is the best values for weight and bias. Okay, so what we will basically do is we will randomly initiate some value for weight and bias, and we will check how well our model is performing. So we will compare the values predicted by our model with the true values, and we will see how many errors our model is making. So based on that information, we will try to optimize our model using gradient descent. So how we will do that is we will try to find the loss function for different weight value and bias value. So if for a particular weight value and bias value the loss function is minimum, then we can say that our model is making accurate prediction. So our goal is that we have to minimize this loss function in every step. So we will randomly initialize some value, and we will reiterate or we will make the model to go through the data again and again, and this process is called as reiteration. So in each step we will try to change the value of weight and bias, and we will try to find the loss function value. So this is how gradient descent basically works, and by doing this you will get the optimized or the best values for your parameters, and this is the formula for updating your weight and bias. So the first equation is used in order to update your weight value, and the second equation represented here is used to update your bias value, and you can read this formula here. So w is equal to w minus alpha into dw, where w is the w in this left hand side is your updated weight, and w in this right hand side is your previous weight. And you can see this alpha, so alpha is your learning rate. So learning rate is nothing but how much change do you want to give to your weight or bias. Okay, so as I've told you, in each step we will change this weight value and bias value, and this learning rate is like the magnitude of change you want to give to your weight and bias. And the dw and db are the derivatives. So we have already discussed about all these things. Okay, so I'm just giving you a quick recap of all those things before getting started. So dw is the dw and db are the derivatives, and we have separate formulas for dw and db as well. So I'll just show you here. So we have discussed all these things in my previous video. So these are called as the gradients. So we have a condition here. So this, if this condition is satisfied, we take this as our dw value and this as our db value. If this condition is not satisfied, then we will take this particular function or formula as our dw and this as our db values, and this is the same formula in order to update your weight and bias. So we have discussed all these things. Okay, and here I have given the definition of a learning rate. So learning rate is a tuning parameter in an optimization algorithm that determines the step size. Step size is nothing but how much change do you want to give to your parameters. Okay, so at each iteration we're moving towards a minimum of a loss function. As I've told you, our goal is to minimize this loss function. So minimum loss function means the value predicted by your model is close to the true value. So that means you have a minimum loss function, which means that your model is making accurate prediction, which is what we want. Okay, so our goal is to minimize this loss function, and for this we implement this gradient descent algorithm. Okay, so this is how we are going to build this SPM classifier. So first of all, we will try to build this hyperplane equation, and then we will try to build the gradient descent equation. Okay, so let's get started. And the first step that we are going to do is import the NumPy library. So this is the only library we will be using in order to build this algorithm or this SPM classifier. So I'll make a text here as importing the dependencies. So let me make a text here as importing NumPy library. So let's import NumPy as np. So most of you, would be having experience working on NumPy library. For those who haven't heard about this, so NumPy library is used in order to make arrays. So we call this arrays as NumPy arrays, and we are importing this NumPy library in the short form as np. Okay, and now let's build our SPM classifier. I'll make another text here as support vector machine classifier. Okay, so you can see the equation of this SPM classifier. So in my previous videos I have we took the bias value as positive, but in some cases we take this bias value as negative. So I'll explain you that. So let's say that we have two cases. So this is the first case. So we have two kind of data points here. So the green colored circles represent one type of data, and the red color circles represent another kind of data. So in this case you can this distance is called as our bias value. As you can see here, this is in the negative side of this x1 axis, and in this case the bias will be negative if we have a hyperplane like this. So in this case, this is another hyperplane, another data set. In this case, the bias value is positive because it is towards the positive side of the x1 axis. So we will generally take the bias value as negative. So that's why we are taking bias values as negative, because like this is the equation we generally use. Okay, so we have to write this equation, this y is equal to wx minus b equation. So we need to build all this weights, bias, and all those things, and after that we will build this gradient descent. Okay, where we will try to include all these formulas in our code. So let's see how we can do that. So how we will create our SPM classifier is that we will create a class. So let's name this class as SPM underscore classifier. Okay, so SPM classifier. So you need to mention parentheses here. So first of all, we need to understand what is meant by this class. So this class in Python is generally used for creating objects. So here we are creating an object called as SVM classifier, and class is used to create a template for this particular object. Let's say that we want to build a car. So this car, you can consider this particular car as an object, and before building this car, you need a template for this, right? So whatever the object or whatever the machine you are building, you need a template for this, and you can consider this template as the class. So we are creating an SPM classifier, and we need to give some template or prototype to this object, and we will include all those template in this class. So this is the importance of class, okay, in Python. So within this class, we can mention different functions. So first of all, let's try to create the skeleton for this SVM classifier. Okay, so skeleton in the sense we are going to see what are the functions that we are going to need. So the first function that I'm going to create is the init function. So this init function is basically used to declare some parameter values, hyperparameters. So we have seen this learning rate, right? So learning rate is one of the hyperparameters for our model. And then we have other hyperparameters like number of iterations and so on. So we will use this init function in order to create this hyperparameters. So I'll explain you in a minute what is meant by this hyperparameter. Just hang in there, okay? And the next function that we are going to create is our fit function. So I'm creating a fit function, and the third function that we need is define. So def, this def stands for define, and this is the keyword in Python in order to create functions. Okay, and each of this define represents each function. So totally we need a fourth function for this SVM classifier, and the third function will be update weights function. Update weights. And the last function that we will need is the predict function. So define predict. So these are the four functions that we have, and let's try to understand what is the purpose of all these four functions. First, we have this init function. So init stands for initiation. So first of all, we will try to initiate some parameters for our model, and after that, we have fit function. So in this particular fit function, we will try to fit the data set to our model. Okay. So once we complete this SPM code, what we will do is we will use the code in order to find whether a person has diabetes or not. So we have already worked on this diabetes dataset. So it contains multiple columns, and finally we have this outcome column here. So this outcome column is your target column, where if the value is 1, that means a person has diabetes. If the value is 0, that means the person does not have diabetes. Okay. And all the other columns, so all the columns except this output column, are called as the input features. So you can consider all these columns as from A to H. So you can consider all these columns as your x-axis value and your I column as your y-axis value. So it is just like taking the x-axis value and y-axis value and fitting it to a line. So that is the purpose of this fit function. So we will create a function so that we can fit our SPM classifier to the data set that we have. In this case, the data set that we have is this diabetes data. So you can use any data set. So in this case, we are going to consider this data set, and now we will build this fit function where we can feed the data set to this particular function. And once we do that, it will try to fit the data set to the SPM classifier that we are building. Okay, so that is the purpose of this fit function. And then we have the update weights function. So as I've already told you, we will randomly initiate the weight value and bias value, and after that we need to reiterate over the data. So the model goes through the data again and again, and in each step we will try to update the weight value and bias value. Update in the sense we will try to change the weight value and bias value by a certain magnitude. So that is done by this update weights function. And finally we have this predict function. So the reason for having this predict function is that once you train your model, if you give new values, let's say that we are giving all the values from this A to H, pregnancies, glucose level, and so on up to this age column, our model should predict whether that person has diabetes or not. So it should give the value as either 1 or 0, 1 being a person with diabetes and 0 being a person without diabetes. So our model has to predict the outcome, right? And we need this predict function in order to find that output. So these are the four functions that we need. So the first function is for initiating parameters, second function is for fitting the dataset to our model, third function, which is update weights, is used for updating the weight and bias through gradient descent. And finally, the predict function is used for predicting the target column. Okay, in this case, whether the person has diabetes or not. So it can be any data set of your choice. Okay, so these are the functions that we have. And I'll just make some comments here so that it's clear for you. Okay, so this function is used for initiating the hyperparameters. So the hyperparameters that we have are learning rate and number of iterations. So let's come to that later. So I'll just make another comment here. This is for fitting the data set to SPM classifier. So this is one of the important functions that we need. And then we have the update weights function, which is used to function for updating the weights or the weight and bias value. Okay, so this is where we will use all these equations. So the equations and the formulas we have. So we will use this gradient equation and updating weight functions in this particular part. Okay, so in this update weights, and finally we have this predict function, and the purpose of this predict function is to predict the label. Okay, so the label being 1 or 0. So predict the label for given input value. Okay, so input value will be all those things. So except this output column, we will give all other values, and our model will predict what is the output, whether it is 1 or 0, which is basically a person with or without diabetes. Okay, so these are the four functions that we need. So we have the skeleton ready, and now we can complete each of this function separately. So in this case, we are going to have three parameters. Okay, so we will be creating our learning rate, number of iterations, and lambda parameter. Okay, so before that, we need to give an inbuilt parameter in all this case, which is called as self. Okay, so you can include this self in all the functions that we have. Self and predict is also self. So the reason we have this self is that, so let's say that we are implementing this svm classifier. Let us say that we have completed this svm classifier and now we want to use it in order to train a particular data set. So in that case, what we will do is, so I will create a variable like model. So in this model, I will call this svm classifier class. So I will write this as svm classifier. Okay, and I'll mention my parentheses there, and within this I will give some parameters. Okay, and this is called as instance. So this model is called as the instance of this svm classifier, and this self takes the value of this instance. So this self basically means the term model. Okay, so whenever we are implementing this svm classifier, once we complete this class, we will call an instance of this model, and this instance is represented as self within this particular class. So when we use a model from sklearn also, we will try to create an instance of some model. So in sklearn, you have different models like logistic regression, linear regression, support vector machine, etc. So when we are calling those models, those like machine learning models, we will create some instance, and this instance is represented as self within this class. Okay, so that is the importance of having this self parameter in all the functions. So it is like one of the inbuilt things that we have to do. Now we need to mention the parameters that we want to declare. So there are three parameters in this case, and they are learning rate, number of iterations, and the third is the lambda parameter. Okay, so these are the three parameters that we need. So let's try to understand this. So learning rate is nothing but the amount of change you want to impart to your weight and bias. So as I have explained it before, so we have the definition for it also. And then we have the number of iterations. So number of iteration basically tells you how many times you want your model to go through the data. So we will be giving the number of iterations value as 100 or 1000 or 10,000. So basically, like if you give the value of number of iterations as 1000, so what that means is your model will go through the data 1000 different times, and each time it goes through the data set, it will try to change the weight value and bias value. So that is represented by this number of iterations. And we have discussed about this lambda parameter in our previous video. So you can see this lambda value here. So this is called as the regularization parameter. Okay, so I have explained you the importance of this lambda parameter in my previous video. So I don't want to go through it again and again. Okay, so these are the three parameters that we have, and we give the learning rate value as 0.01 or 0.001 and so on, and lambda parameter will also be like a 0.01 and so on. So you can manually tweak all these values and see how your model is performing. Okay, and you can give number of iterations as a 100,000 or 10,000, any number you want. Okay, so these are the hyper parameters that we have, which you can manually give. So these three parameters are called as hyper parameters, and weight and bias, this W and B, are called as your model parameters, because these are the parameters of your model. So these are internal parameters, but these parameters work beyond the model or outside the model. So we manually give this value, but we cannot manually give the values for weight and bias. Hence, these are called as the model parameters, and these are called as the hyperparameters. Okay, so now we need to initiate all these parameters. So how we will do that is by mentioning self dot learning rate. So self dot learning rate is equal to learning rate, and self dot number of iterations. I'll explain you what happens here exactly, so just a minute. So self dot number of iterations is equal to, again, number of iterations, and self dot lambda parameter, which is basically the regularization parameter, is equal to lambda parameter. So lambda is a keyword in Python, so it represents another function, so we cannot write only lambda. So hence I'm naming this as lambda parameter. Okay, so lambda parameter. So this is how you can initiate the hyper parameters. So what basically happens here is, when we call this SVM classifier. So as I've told you, let's say that we have completed this SVM classifier and now I want to call this. So I'll create an instance as model and I will write model is equal to SVM classifier, which is basically the name of the class that we have created. So SVM classifier. And within this parenthesis, we need to give all these three parameters. The parameters are learning rate, number of iterations, and lambda parameter. So I will write all those things. So I'll just copy all those things from here. So what we will do is, so while calling this in this parameter, we need to give the learning rate value. Let's say that the learning rate value is 0.001, and let's say that the number of iterations, so the number of times we want our model to go through the data set is 1000. So the model will go through the data 1000 times, and the lambda parameter is, it can be 0.01 or any number. So we will give all those values. So model is equal to SVM classifier, and these are the parameters. So you can see here self dot learning rate. As I've told you, this self is nothing but the instance of your model. In this case, the instance is nothing but this variable called as model, right? Now, when you mention self dot learning rate, what it basically means is model dot learning rate, which is equal to 0.001, and self dot number of iterations is nothing but model dot number of iterations, which is given by this 1000, and finally self dot lambda parameter is model dot lambda parameter, which value is 0.01. So that's what we are doing here. So we need to initiate this parameter like this, and we will give all those values while we are calling this model, while we are implementing this model. Okay, so this is how we will do it. Now we can go on to the next function, and this next function is a fit function, right? And the purpose of this fit function is to fit our dataset to our SVM classifier. So for that we need two variables, so self dot m and self dot n. Self dot n is equal to x dot shape. So before that we need to give two parameters in this fit function. So the two parameters are x and y. So self is the parameter which we give as an inbuilt function, so self, and then we have x and y. So x is nothing but all the input features, so all the input features are from a to h. Okay, and so this represents your x-axis value, or basically the x value, and your outcome column represents your y value. So we need to mention x and y. So when we call this fit function, we will feed this data set, this x and y data set, to our model, and that's why we need to mention x and y in our fit function. Okay, so now we need to understand what is meant by this m and n. So your m basically represents the total number of data points that you have, and n represents the total number of input features that you have. Okay, so let me mention that in some comments here. So m is your number of data points in your data set. Okay, so number of data points, and you can also call this as number of rows. And now let's try to understand what is our n. So I'll just copy this and I'll paste this here, and this will be your n. So let's try to understand what is this n value. So n value is basically the number of input features that you have. So number of input features, and in other words, it is nothing but your number of columns. So let's try to understand this. So we have a data set here, right? So we have taken a sample data set here, and it contains some amount of data. Now let's try to find how many rows are there. So this particular data set contains about, I think it contains around 700 data points. So yeah, it contains about 769 data points. So what basically it means is we totally have 769 rows, and each row represent the data for each individual. Okay, so this means this is the data from 769 different people, and we call all these rows as individual data points. Okay, so that is represented by your value m. Okay, so m basically is your number of data points or your number of rows, and n is the number of columns that we have. Okay, so we don't take this output column. So excluding this outcome column or the target column, how many columns that you have? So totally we have, so totally we have 8 columns, right? So all these 8 columns is your number of input features. So totally we have number of 8 input features, and the total number of input features is n. Okay, so in other words, you can say these are the number of columns. So the reason we want to find this is, so we have already discussed about this weight, right? So number of weight that you have in a particular model is equal to the total number of input features that you have. So in this case, you totally have 8 input features, right? So don't consider this outcome column. This is target column. This is different. This is y value, right? So your number of weight value. So if you have 8 different input features, so in this case you have 8 different weight values for your model. So in case, let's say that you have 20 input features or 20 different columns, in that case your model have 20 different weight values. So basically weight is like an array. Okay, so this particular, so weight is an array, and this array contains the number of values which is equal to the total number of input features that you have. So it is basically equal to the number of columns that you have in your data set. Okay, so that is the importance of finding this number of columns in a data set. So m represents the total number of rows and n represents the total number of columns. And the reason for finding this n is we need to know how many weight values are there. Okay, so that's why we are finding this particular n value. So you can find this by x dot shape. So x dot shape is nothing but what is the shape of your x. So if you consider this, so this is our x, right? So it will the shape of this particular x will be 769 into 8, where 769 represents the total number of rows and 8 represents the number of columns a to h. Okay, so that is what we will get from this x dot shape. So this x dot shape will give you an output of 769 into 8, and m will take the value as 769 and n will take the value as 8. Okay, so that is what we are basically doing. We are trying to find the number of data points and the total number of input features that you have. Now the next step that we are going to do is we need to initiate the weight value and bias value. So initiating the weight value and bias value. So as I've told you earlier, first we will give some random value for our weight and bias. So what value we will generally give us, we will just give the value as 0. So we will do that using the same method. So I'll mention self.w. Okay, this basically represents model.w is equal to np.zeros. So this is why we need the numpy array. Okay, so just a second. Yeah, so np dot zeros. So and the shape of this array should be self dot n. So what we are basically doing here is I'm initiating the value of this w, which is my weight value, and I'm creating it as a numpy array, because we know that weight is basically an array and the number of values in this array is equal to the total number of input features, which is n. So that's why we are mentioning this self dot n. So I want to create a numpy array and all the values inside this numpy array should be 0. So that's why I'm mentioning np.0. So np.zeros is a function that will create you a numpy array, and all the values will be 0 in this numpy array, and the shape of this particular array is n. Okay, so as I've told you, this basically means it will try to find how many columns are there in a data set, and based on that value it will create as many weight values, and all the values will be 0. So that this is how we will initiate weight value, and then we need to initiate the bias value. So self dot b, so b is our bias value, and we will just give the bias value as 0. So the one main thing you need to note here is weight is generally an array. Okay, so it contains multiple values, whereas bias is a single value, it is like a single real number value, whereas weight is an array. So that's why we are initiating the bias value as just 0, but we are initiating the weight value as a numpy array because it is basically an array. Okay, and then we need to mention this x and y. So self dot x is equal to x, and self dot y is equal to y. So x is nothing but all these 8 columns from a to h, and y is our outcome column. Okay, so we will feed this data set to our model in a later part of the code. So this is how you can initiate weight and bias value, and this is how you can represent this x and y value. So x is all my input features and y is my output column. So once we initiated all these values, now what we need to do is build our gradient descent algorithm. As I've told you, so we need to build this equation, and after that we need to find the optimum values for weight and bias, right? So first we will initiate the value. So in this case we are initiating with the value 0, numpy.zeros, and for bias we are just taking 0. So after that we are going to build this gradient descent. So what we will do is we will take this initial value and we will try to make some prediction, and this gradient descent we'll try to compare the loss function for different weight value and bias value. Okay, so if you remember, we have discussed this in the previous case. Okay, so I'll just take this particular slide. So let's take this cost function. So cost function and loss function are not something very different. So if you take the difference between the true value and the predicted value for one single data point, that is called as the loss function, and if you do that for the entire data set, it is called as cost function. So that is the difference between it. Okay, so we have the cost function in the y-axis and weight in the x-axis. Let's say that we are initiating some random weight value. So in our code, we have initiated the random value as 0, right? So this is our random initial value, and let's say that for this particular weight value, we have an higher cost function. Okay, and this is the point. So this point is called as global minimum, and at this point, if you consider the weight value at this particular point, your cost function value will be minimum. So you can just take the corresponding y-axis value. So it is very minimum, right, compared to this particular value where the cost function value is minimum. And our goal is to minimize this cost function. So we will try to change the weight value regularly until we reach this global minimum. Okay, so that's what we are doing here. So we will take a random initial value and we will implement this gradient descent in order to reach the global minimum where the loss function or the cost function value is minimum. And that's what we are going to do here now. So I'll create a text here as implementing gradient descent algorithm. Gradient descent algorithm for optimization. So optimization in the sense we are going to find the optimized value for our weight and bias. Okay. So for this we need to create a for loop. So let's create a for loop as for I in range number of iterations. So we need to mention it as self dot number of iterations. Okay, so basically what this means is, as I have told you before, we need to give some number of iterations for our model. So in this example, we took the number of iterations as 1000, right? So it means your model will go through the data 1000 times, and each time it will try to impart some change to this weight value and bias value. So that's what we are going to do in this particular for loop. So when I mention this number of iterations, so this value will be 1000 in this case. So you can give any values, 1000, 2000 or anything. So your for loop will run 1000 times, and each time it will try to update your weight value and bias value, and that's what we are going to do now. So I'm going to call this self dot update weights function. Okay, so update weights function. So this update weight function is what we are going to build now. So first of all, I'm trying to initiate the hyperparameters like learning rate, number of iterations, and I'm also initiating the lambda parameter, which is my regularization parameter. So after that, I'm creating a fit function in order to fit my x and y to my svm classifier, and I'm trying to find the m and n value, where m is the number of data points and n is the number of columns that we have, and then we are initiating weight value as a numpy dot zeros, which is basically a numpy array with all the values as 0 and bias value as 0. After that, we are implementing the gradient descent, where we are creating a for loop with the number of iterations mentioned by the user. And within this for loop, we need to update weight. So what we are doing is we are updating the weight each time the for loop is running. In other words, each time the model goes through the data, it will try to change the weight value and bias value so that we get accurate predictions from our model. Okay, so that's what we are doing here. And now we can come to our update weights function. Okay, so we have created this update weight function, and now we need to build this update weights function. So the first thing I am going to do here is y label. I'm going to create a variable called as y label, and this label is equal to np.var self dot y less than or equal to 0. I'll explain you in a minute what we are basically doing here. -1 comma +1. So you can just call this part as label encoding. So I'll call this as label encoding. So we know that we have the y-axis value. Your y-axis value is nothing but your outcome column or target column, where 1 represents a person with diabetes and 0 represents a person without diabetes, right? So this is the label we generally deal with in machine learning. We take the label values as either 0 or 1, right? But if you remember the things we have discussed in my previous videos, support vector machine will try to find whether the label is +1 or -1. Okay, so if you come to this particular slide, So what we will basically try to do is we will try to find this y cap value. Y cap value is nothing but your label value, and this label value will be either 1 or -1. If the value is +1, then we can say that a new data point lies, or the new data points belong to this group of data. Or else if the label value is -1, we can say that the new data point lies to this green colored group of data. Okay, so generally support vector machine works like that, whereas in the case of logistic regression we take the label values as 0 or 1, right? And it is the general way of having label values in any data set, so it's either 1 or 0. But support vector machine, we will give the label values as +1 or -1 because it is the convenient way for it. So you will basically get some negative value or positive value. Let's say that you are getting the label value as -1, so then it will try to say that it belongs to this group of data, this green color group. And if the value is +1, it will tell that it belongs to this group of data. So we need to do that label encoding. So what I'm doing here is, if the label value is 0, I want to convert all the values to -1. Okay, if the label or else in other case the label value will be 1. Okay, so that's what we are mentioning here. So I'm trying to look at the y-axis value, and what I'm telling here is, if the value is 1, you don't need to give any change. If the value is 0, you need to convert it to -1, so that we can have convenient labels for our SVM classifier, because 0 and 1 does not work well with SVM. So we need +1 or -1 for our SVM, and that's why we are using this np.var. So what this np.var function basically tells us, it will try to find this condition. So in this condition, the condition here is y should be less than or equal to 0. So if y is equal to 0, then we can say that we want to convert all those values by -1, or else the value can be +1. Okay, so that's what we are doing here. We are basically label encoding. So we are converting all the zeros as -1, and all the +1 will stay as +1. Okay, and now we are going to create another for loop, and this for loop is for index comma xi in enumerate self.x. Okay, so let's try to understand what is what we are trying to accomplish in another for loop. So for our gradients, we have two set of formulas, right? So I have showed you already. So we have discussed about this in our previous videos. So we have a condition. So this condition has to be satisfied. So yi into wxi minus b. If this value is greater than or equal to 1, we take these two formulas for our gradients. Or else, if this condition is not satisfied, which is the condition given here, so in that case, the formula will change slightly. So this will be the formula for my dw, and this will be the formula for my db. So we have a condition and we have two sets of formula, and now we need to include this condition. So yi basically means the individual yi values, which is either 1 or 0. Okay, and xi represents individual rows. So we have to take this individual label value either 1 or 0, and now we have to take this individual row value, and now we need to multiply it with the weight, and subtract it with the bias value, and then we need to multiply it with the yi value. If that particular value is greater than or equal to 1, then we have this formula, or else on the other condition we have this formula. Okay, and this is what now we are going to do this in this particular for loop. So I'll explain you what does this enumerate function does, but I'll just complete this next line of code. So this is for carrying out my condition. So my condition is that is equal to y label. Okay, so y label of index. So y label of index is nothing but your yi. Okay, so this yi is what I am representing as y dash label. So y underscore label is nothing but this value. So if you remember, like I've taken all these values and I've converted all the zeros into -1, and +1 stays as +1, right? So this is my y underscore label. The only difference is that all the zeros will be converted to -1. So that is my y label. So it contains all the label values, and I'm taking all the values individually because my condition wants all the individual label values. So yi, right? So that is what I am doing. So y label index into, so we need to multiply it with np dot dot. So this is just like a dot product of w and x. So xi and self dot w. So self dot w, which is the product of my weight and my xi value, minus self dot b, and this should be greater than or equal to 1. So this is my condition. So this line is nothing but the condition that I have explained you here. So I have taken this condition and I have represented it here in Python. Okay, so condition is equal to y underscore label index. So I'm taking all the individual labels and I'm taking the corresponding xi value. So xi is nothing but all the input features, and here we are multiplying xi and w, and then we are separating by the bias value, right? So that's what we are doing here. So we are taking the numpy dot, so this is like a matrix product. So xi comma self dot w minus self dot b, so it is just the same equation, and this should be greater than or equal to 1. Okay, so what we are basically doing is, in this case, so let's come to our data set. Let's say that we have this sixth column. So in this case, what I will do is I will take the yi value. So this is my yi value now. So the yi value is 1, and this y underscore label index will take the value as 1. Okay, and I'll take the xi value. So xi values in this case is all these 8 values. So I will take all these values and I will multiply all this xi value with my self dot w, subtract it with my self dot b, and then I will multiply it with y underscore label index, which is the value is 1. We know that, right? And I will check whether that value is greater than or equal to 1. So this is my condition. So now the reason we are using this enumerate function is, so enumerate is an interesting function that we have in Python. So let's try to understand what does this enumerate function does. So I'll explain to you in a simple way. So I'll create another cell. In this case, let's create a list as my list. So we are creating a list here basically, and let's say that this list contains the values like 10, 20, 30, 40, and 50. Okay, so these are the 5 values in my list. Just a second. Okay, so now what I'm going to do is, for I'll name this as, I don't want to interpret this interrupt this particular code. So I'll name this as for I comma my list I in enumerate my list. So the reason I'm just doing this is in order to explain you the importance of this enumerate function with this for loop. Okay, and I want to print I and my list. So enumerate is basically like a counter. It will count how many times a particular operation is carried out on a list. So I'll run this. Let's see what are the values that we are getting. Okay. So just a second. I just wanted to change one thing. So for I comma my list I in enumerate. Okay. So my list I, just a small change. Now let's try to understand what this enumerate does. So we are creating two variables for this particular for loop. One is I and the second is my list I. Okay, so what I want to do is I want to take this list and then I want to print the index of the number and its particular value. So the index of this 10 is 0. The index of this value is 1. This is 2, and so on. So we know that in Python indexing starts from 0, right? So the first value will have the index as 0, the next value is 1 and 2, and so on. So now I want to get the index value as well as the particular element value. So if you see here, the index of this value 10 is 0, and for 20 the index is 1, for 30 index is 2, and so on. So I want to take both index value and the element value, and you can do that by this particular enumerate function. So if you do that, this particular I, the first variable, will get the index of the values, and the my list I will get the corresponding element value 10. So that's what we are doing here in this particular case. So I'm creating two variables here. So I'm creating the first variable as index and the second variable as xi. Okay, so when I do this, what happens is, let's say that I have this x. So I'll just remove this for some time. So this is my x now, right? So when I carry out this for loop along with the enumerate, so what happens is, first of all, it will go through this. It will try to find the index of this particular data point, and it will try to take all this values. So all these values is nothing but xi, and the corresponding index will be 0. So as we have seen here, so when you run this for loop will go through the entire data set. So it will go through all the rows and it will try to get the index of the particular row and all the values in that row. So this index basically will take the value of that index, and xi will be all the 8 values for individual rows. Okay, so that's what we are trying to do here. And in order to find that index as well as the value, we use this enumerate function. So it is not, I think there is a spelling mistake here, so we need enumerate. Okay, so this is the function we need. So it basically gives you the index as well as the element of that. So enumerate actually works as a counter. So it is not like it gives the index of the value, but it is just like a counter. But we can use it in this case as well in order to get the index as well as the element. Okay, so the reason I want to get all the xi values individually is that I want the y label value and the xi label value, right? So I want to take, so if you come to this formula, so we have this yi. So yi is nothing but all the individual y values, and xi is nothing but all the individual x values. So I will take all this x value, and then I will take the outcome value, right? So outcome value is will be either 1 or -1. So I need to do that. So for that particular reason, and I'm finding the index of a particular row, and then I'm finding the xi of that particular row, and I'm doing this particular condition. Okay, so once we satisfy this condition, we can build our gradients formula. Okay, so we have the if condition here, right? So if this condition is satisfied, if this condition is true, I want this particular formula for my gradient. So that's what I'm going to do now. So if you don't understand few things, don't worry. So once I complete the code, I'll just give you a quick recap of what how things happen here, and in that case you can understand everything completely. Just wait for all the things to complete. So now I'm going to create a if condition. So if condition is equal to true, so this basically means if this particular condition is satisfied. So I'm taking the same variable condition. If this condition is satisfied, then I want the gradients formula to be, or the derivatives formula to be, so you can call them as both. So they are nothing but gradients or the derivatives. So these are nothing but my dj divided by dw. So this is nothing but how much your cost function values change if your weight changes. So dj by db represents how much your cost function changes when your bias change. So that is the importance of these two values. So here the formula is 2 into lambda into weight, right? So we need to write that. So let dw be our gradient for weight, and dw is equal to 2 into self dot learning parameter. It's lambda parameter. Okay, so it's lambda parameter into self dot w. So this is nothing but my this particular formula. So dj by dw, which I have represented just as dw, is equal to 2 into lambda into w. So that's what I have written here, 2 into self dot lambda parameter into w, and my db value is just 0, right? So you can see the formula here. So dj by db is equal to 0. So if this condition is not satisfied, we need this particular formula. Okay, now let's include that formula as well. So if the condition is satisfied, we have this particular equations, and if this condition is not satisfied, which is represented by else we have dw is equal to 2 into self dot lambda parameter and into self dot w minus np dot xi comma y label index. Okay, and your db value will be y label index. Okay, so this is nothing but the formula that we have if the condition is not satisfied. So dj by dw in this case is 2 into lambda into w minus yi into xi, and dj by db is yi. Okay, so I'll just make a text here as, or else a comment as gradients. Okay, so this part of the code is to build the gradient. So I'll just mention this as gradient. So gradients are nothing but your dw value and the db value, which we need for our gradient and descent model. Okay, so we have dw and db value, right? So we can find this value by this particular formulas. So we have two set of formulas for dw and db. So if the condition is satisfied, this particular condition is satisfied, we take this formulas, and if this condition is not satisfied, we will take this particular formula. And the reason we are running this in enumerate is we will take all the data points individually. So we will take the y underscore label, so we take the label values and the corresponding xi, which is the input features value, and then we will try to find this condition is satisfied or not. So if this condition is satisfied, we have these two formulas for dw and db. If this condition is not satisfied, we will take the formulas as dw and db. Okay, so now once we have this, we need to build these two formulas. So we have this is the final gradient descent formulas for updating the weight and bias value. Okay, so now we need to write these two formulas. Now all the things are very easy from now on. Okay, so these are basic things. So I will just come out of this iteration. So make sure that you are not in the sales iterations. So it should be in this particular line. So self dot w is equal to self dot w minus self dot learning rate. So whenever you are mentioning the parameters within this class, you need to mention self. So that is the importance of it. So self dot learning rate into dw, and for updating the bias, it's the same. So self dot b is equal to self dot b minus self dot learning rate into db. Okay, so just a second. So this is the formula for updating our weight and bias value. So this is our gradient descent. So w is equal to w minus learning rate into dw, and the dw value is given by these two equations. Okay, and now we finally completed our gradient descent, and now we can write the function for predict. Okay, so for this I'm going to create a variable called as output. So now what happens is, once this gradient descent is completed, you will get the best weight value and your best bias value. Okay, so we get optimized values for our weight and bias. Now you have this equation y is equal to wx minus b. So initially we took the values for w as numpy zeros and b as a single zero number, right? So and after that we will run our gradient descent in order to find the best value for weight and bias. Now we have the best value for weight and bias, and now if you give the xi value, your model can predict the y value, whether the value is -1 or +1. So it can make that predictions, and that's what we are going to do in this particular predict function. So output, so we are creating a variable as output, and np dot dot. Okay, so np dot dot x comma self dot w. So we need to mention another parameter here. So predict x. So the reason is, so when you give a new x value, so when you give all this value, your model can predict what is the outcome. So you need to give this x value to this predict function. So that's why we need to mention it here. Okay, so x self dot, so self dot w x comma self dot w minus self dot b. So this is nothing but the equation of your hyperplane. Okay, so wx minus b, so that's what we are mentioning here. So as w and x are nothing but arrays, so they are not single numbers, so we need to multiply it using np dot dot. So this is just like matrix multiplication. Okay, so output is equal to np dot dot x comma self dot b minus self dot b, and we have the predicted labels. So the value you will get won't be either +1 or -1. So the value can be anything. So the value you get can be +1, +4, +5, or it can be -3, -6, -1, and so on. So it can be any values. Now we need to round those values. So I'll create another variable as predicted labels, and now I'm going to round all the values. So if we get a negative number, then we will say that that particular value is -1. So I'll just complete this, and then you will understand what I'm doing here. So predicted labels is equal to np dot signs, np dot sign of output. Okay, so what we are doing is, as I've told you, in logistic regression, when we do this predict function, it will output the value as either 0 or 1. So the value will lie between the 0 or 1. But in this case, the value you get using this particular formula won't be either 0 or 1, or it won't be either plus 1 or minus 1. So this value can be anything. So it can be any positive number or any negative number. So we need to generalize this. So if it is a negative number, so it can be any negative number. It can be -1, -3, -6, -10, -100, any number, and so on. So if it is a negative number, then we need to say that that value will be -1. If the value, this particular output value is +1, so it can be +1, +5, +10, +100, so on. In that case, we will take the value as +1. So that's what we are doing that by np.sign. So the reason is that in SVM we are interested in whether that label is positive or negative. If the label we are getting is a positive value, then it is one group of data. If the label we are getting is negative, then it represents another group of data. Okay, so that's what we have mentioned here. So you can refer this particular equation. So yi, so if this value is less than or equal to -1, in that case we will take that as -1. If the value is greater than or equal to +1, we will take that as -1. So it doesn't mean that your label has to be +1 or -1. So it can be any values, but we are interested in whether that value is plus or minus, whether it is a positive number or a negative number, and we can find that using np.sign. So when you use this np.sign, it will go through this output value. If it is a positive value, it will output the value as +1. If it is a negative value, it will give the output as -1. Okay, so the final value, so this predicted labels, so this particular array will contain all the values as +1 or -1, whereas output can contain any values. So this particular list can contain any values, but this predicted labels will contain the values either +1 or -1, because we are just considering the signs. And now we just have only one more thing to do. So that is, if you remember previously, we have converted all the zeros as -1, right? So, and we didn't make any changes for 1, but we have changed all the values of zeros as -1, right? And now we need to revert this particular change. Now we need to take this and we need to change all the -1 back to 0. So that's what we are going to do now. So I'll call this as y at. So this is my final predictions. Okay, so this should contain the values as either 0 or 1, because these are the two true labels that we have. Okay, so y at is equal to np dot where. So I'm just reverting that particular change. Predicted labels, and it should be less than or equal to -1, 0, comma 1. So basically what I'm doing is, if that value is equal to or less than -1, I want to change it to 0, or else it should be 1. So what I'm basically telling here is, so all the values which is -1 should be changed to 0, and all the +1 can stay as +1. So we are just removing this particular change that we have done here, because our original dataset contains the values as either 1 or 0. And if you don't do this, if you don't revert back this change, then your accuracy score won't be working properly. So you don't need the labels to be +1 or -1. So you need the labels to be 0 or 1. So that's what we are doing here. So this is our final step, and finally we can return our y at value. So finally we can return y at. So when you run this predict function, it will try to return you this y at value, which will be either 1 or 0. So this is our entire code. So I know that you may not understand few things, but I'll just give you a quick recap of all the things that we have done here, and now you can understand all the things that we have done. Okay, so first of all, the idea here is, we have the equation of the hyperplane, which is y is equal to wx minus b, right? So that is what we have mentioned in this defined predict. So np dot x comma self dot b. So this is nothing but w into x minus self dot b. Now we need to find what is the best value for our weight and bias, and for this purpose we need to build our gradient descent formula, or gradient descent algorithm. And this is the formula for updating our weights, which is w is equal to w minus alpha into dw, where alpha is your learning rate, and the formula is same for bias as well. Now we know the formula for dw and db, right? So the only challenging part is that we have a condition here. So if this particular condition is satisfied, we can take these two formulas. If this condition is not satisfied, then we need to take these two formulas. So that's what we are basically doing here. So first of all, I have imported my NumPy library, the basic thing, and then I'm creating a SVM classifier. So this is my support vector machine classifier model, and I have four functions here. So first is my init function, and then we have our fit function. The third function is our update weights function. Finally, we have predict function. So the purpose of this init function is used to initiate some parameters. So the parameters that we are initiating are learning rate. So learning rate is nothing but what is the amount of change do you want to give to your weight and bias when you are running your gradient descent. And number of iterations is the number of times you want your model to go through the data, and lambda parameter is your regularization parameter. So we have initiated all these parameters here. Self is nothing but the instance we are creating. So in this case the instance is nothing but model. So there we can give any values for our learning rate, number of iterations, and lambda parameters, and then we have initiated all these parameters. So the second step is fitting our data set to our classifier model. Okay, so we need x value and y value. So the x value will be all the 8 columns, all the input features, and all the y value will be this particular output column. Okay, so this is our second function, and we are trying to find the value for our m and n. So m is nothing but the total number of data points. In other words, it is the total number of rows that we have, and n is the total number of input feature, or in other words, it is nothing but the number of columns. So the importance of n value is that the number of weight values you have for a model is equal to the number of input features that you have. In this case, you have 8 input feature from this pregnancy column to this age column. So totally you will have 8 different weight values. Okay, so this is how we will initiate weight value and bias value. So weight will basically be a numpy array, and we will initiate with all the values as 0 in the shape of n. So n is nothing but the total number of columns, and as I've told you, the number of weight is equal to the total number of columns that you have, and bias is nothing but we are initiating with 0. So x is my input feature, y is my label. And once we initiate all these parameters, we need gradient descent in order to optimize our model, in order to find the best value for my weight and bias. For that, I'm creating a for loop, and this for loop runs for the number of iterations we have mentioned. If we have mentioned the number of iterations as 100, it will run for 100 times. If you mention it as 1000, it will run for 1000 times. And each time this for loop runs, it will change the weight value and bias value. And that is done by this update weights function, which is our third function. So now we can come to this third function. And now the interesting thing that we are doing is we are converting the labels. So we are converting all the label value 0. If the label value is 0, we are converting it to -1, and all the +1 will stay as +1. Okay, because the labels are convenient in this way for support vector machine, because it will try to find whether the label value is +1 or -1. So it doesn't care whether it is 1 or 0, but it wants to know whether it is +1 or -1. So that is the next step. And then we are using this enumerate function. So the reason for this is in order to carry out this condition, and I have shown you what is the importance of enumerate. It will take a list, and it will try to give the index of a value and the value. So we have 5 elements here. So if you want to enumerate this list, it will take this first value. So it will give the index of this first value, which is 0, and the value itself, which is 10. Okay, so you will get the index and the corresponding value. So we want the index of the data point and the corresponding xi value. So if you go to this data point, the index of this first row will be 0. Okay, so index value will be 0, and the xi value will be from 6 all the way to this 50. Okay, so this is my index and xi value. And once I have this, I can run this condition. So this condition is nothing but the one which we have mentioned here. So we are creating this condition, and if this condition is satisfied, my dw, my gradient formula is 2 into lambda parameter into self dot w. Okay, if this condition is not satisfied, the dw and db value changes. And once we have that, we can implement this gradient descent, the updating weights and bias value functions, and we have represented it here. So this is nothing but w is equal to w minus learning rate into dw. This is b is equal to b minus learning rate into db. So the gradient descent updating weight formulas. And finally, once all these parts are completed, we will get the optimized weight value and bias value. In other words, your model will get the best weight value and bias value. If you consider this weight value and this bias value, what it means is your model can make accurate predictions. So it basically means there is not much difference between the true value and the predicted value. So that is what is done up to this particular mark. After that, you have this equation now. So you have the optimum value for this w, and you have the optimum value for b. And now if you give a new value, if you give a new x value, it will try to find the label, and it will be stored in this output. The main thing you need to remember here is this output need not be either +1 or -1. So it can be any values. So it can be any positive values, it can be any negative values, but we are interested in whether that value is either positive or negative, because this is a classification task, right? So this is not a regression task. We want to find whether the person has diabetes or not. So this is a classification task. And for this, I'm going to use this np.signs, and it will, if the value is negative, it will output the value as -1. If the value is positive, if the value is 1 or +5 or +6, the output will be, final output will be +1, and all those +1 or -1 will be stored in this predicted label. So this is my labels, which contains either +1 or -1. Finally, I have this y at, so I am reverting the change that I have done before. So all the -1 will be changed back to 0, and all the +1 will be the same, +1. So that is what is done by this np.var, and this is my final output, final predicted value. Okay, so this y at, so this is y at is nothing but y cap that we generally write in a convention. So this is my final predicted value. So this will be either 1 or 0. So this is my prediction, where 1 being a person with diabetes or without diabetes. So this is how you can build a support vector machine classifier from scratch in Python. So now you can use this particular code, this particular SVM classifier for any data set. So in this case, we have a diabetes data set, right? So in my next video, I'll explain you how you can implement this support vector machine classifier, how you can use this particular code in order to find whether a person has diabetes or not. So you can use any data set in order to find that particular predictions. Okay, so in this case, we will take this particular data set alone. You can also try this with a different data set. So this is how you can build your SVM classifier from scratch in Python, and I hope you're completely thorough with all the things that we have covered here. So if you don't understand few things, you can mention me in the comments, and I'm sure that if you don't get a few things, you will understand it completely in the next video, where we will take this particular dataset and we can see for ourselves how this particular code works. Okay, so that is all from my side, and I hope everyone is clear up to this particular point, and I'll see you in the next upload. Thanks for watching.